An enduring crimson jewel in our night sky, Mars has captivated human imagination for millennia. Once viewed as a world crisscrossed by canals, a testament to a dying civilization, the red planet has transformed in our understanding into a world of stark, cold beauty. Yet, the ghost of water clings to its rusty dust. For decades, the mantra of Mars exploration has been, "Follow the water." A quest that has led scientists from tantalizing hints to definitive proof of a wetter, warmer past, and now to the hunt for modern, fleeting brines. Our perception of water on Mars began not with scientific data, but with a trick of the light and a mistranslation. In 1877, astronomer Giovanni Schiaparelli mapped the planet, noting long, straight lines he called, quote, canali, which in Italian simply means channels, but in English, it was translated as, quote, canals, implying intelligent construction. This spark was fanned into a flame by American astronomer Percival Lowell. From his observatory in Arizona, Lowell produced intricate maps depicting a planet-wide irrigation system built by intelligent beings to channel water from the polar ice caps to their arid cities. The idea of a populated Mars gripped the public imagination, but as telescopes improved, the canals remained elusive, likely optical illusions created by the brain's tendency to connect faint features. The space age brought a definitive end to the era of canals. NASA's Mariner 4 flyby in 1965 sent back images of a cratered, moon-like surface. The romantic vision of a civilized Mars evaporated. The true revolution came with Mariner 9, the first spacecraft to orbit another planet. Arriving in 1971 amidst a global dust storm, it waited patiently for the haze to clear. The view was transformative. Mariner 9 revealed colossal volcanoes like Olympus Mons, and, most importantly, the first definitive evidence of past water. Its cameras imaged vast, sinuous channels that were unmistakably dried-up riverbeds. It unveiled Valles Marineris, a canyon system dwarfing our Grand Canyon, shaped in part by massive water outflows. The illusion of canals was gone, replaced by the concrete reality of a Mars that was once dynamic and wet. The Viking program in 1976 built upon this. The orbiters provided even more detailed images of catastrophic flood channels. The two landers confirmed water vapor in the atmosphere and found that the soil itself contained chemically bound water, revealing it to be composed of iron-rich clays and minerals that only form in the presence of liquid water. But the Viking landers also created a huge mystery. Their instruments failed to detect any organic molecules in the soil, a major blow to the search for life. It was thought a powerful oxidant in the soil was destroying them, a puzzle that wouldn't be solved for over 30 years. The final piece of this historical puzzle came from the Mars Global Surveyor in 1997. Its high-resolution camera revealed thousands of small, fresh-looking gullies carved into the sides of craters. Their apparent youth suggested liquid water might have flowed in the very recent past, shifting the focus from the ancient past to the tantalizing possibility of liquid water today. To understand why modern water is so exciting, you have to appreciate why it has such a hard time on Mars. The Martian atmosphere is incredibly thin, less than 1% of Earth's pressure. This low pressure means the boiling point of water is just above freezing. If you poured a cup of pure water on Mars, it would simultaneously freeze and boil away. The temperature is the other half of the problem. Mars is frigid, with an average global temperature of -63 degrees Celsius. For the vast majority of the planet, it's far too cold for pure water to exist as a liquid. This combination of low pressure and low temperature means that in many regions of Mars, water ice, when heated, turns directly into vapor, a process called sublimation, without ever becoming a liquid. For liquid water to have a fighting chance today, it needs an accomplice: salt. Anyone who has seen salt spread on an icy road understands the basic principle. Dissolving salt in water disrupts the formation of ice crystals, dramatically lowering the freezing point. This salty water, or brine, can remain liquid at temperatures far below zero. On Mars, this effect is key. The planet's surface is rich in salts, including sulfates, chlorides, and, most importantly, a class of salts called perchlorates. Perchlorates were the surprise discovery of the Phoenix lander, which touched down in the Martian Arctic in 2008. It found significant concentrations of perchlorate in the soil. This discovery was revolutionary. First, it solved the Viking mystery of the missing organics. Perchlorates are powerful oxidants, especially when heated. When the Viking landers heated soil samples, the perchlorates likely incinerated any organics, explaining the strange results. Second, and more crucial to our story, perchlorates are incredibly effective at lowering the freezing point of water. A calcium perchlorate brine, for example, can stay liquid down to a staggering -75 degrees Celsius. This opened up a vast range of conditions where a brine could theoretically exist on Mars. Another critical property of these salts is deliquescence. This is where a salt is so good at attracting water that it can pull water vapor directly out of the atmosphere to form a liquid brine. Even in the thin Martian air, humidity can sometimes get high enough for this to happen. This provides a way to form liquid brines without needing melting ice. With these processes in mind, scientists began looking for modern-day surface features that might be the telltale signature of these fleeting brines. This led to the discovery of the most compelling and most controversial evidence for present-day liquid brines, features known as recurring slope lineae, or RSL, first identified in 2011 from the Mars Reconnaissance Orbiter RSL, are dark, narrow streaks that appear on steep, sun-facing slopes during the warmest Martian seasons. They appear in the spring, grow downslope over the summer, and then fade away in the autumn, only to reappear the next year. This seasonal pattern is precisely what you would expect from the flow of liquid water. In 2015, the connection to brines seemed to be solidified. Scientists announced they had detected the spectral signatures of hydrated perchlorate salts within the RSL, right where and when the streaks were at their widest. This seemed to be the smoking gun. However, a robust scientific debate emerged. While the wet hypothesis posits that RSL are brine flows, an alternative dry hypothesis suggests they are just tiny landslides of sand and dust. A key piece of evidence for the dry model is that the streaks are almost exclusively found on slopes steeper than 27 degrees, and they stop at an angle that perfectly matches the angle of repose for dry sand on Mars. A liquid flow would likely continue onto shallower ground. Furthermore, some scientists now believe the detection of hydrated salts might have been a data artifact. Today, the community is divided. RSL could be wet, dry, or some hybrid damp flow we don't yet understand. While orbiters spot potential flows, we need rovers for ground truth. NASA's Curiosity rover, exploring Gale Crater since 2012, has added crucial pieces to the puzzle. In 2019, it identified sulfate salts in ancient sedimentary rocks, suggesting that as the lake in Gale Crater dried up billions of years ago, it became increasingly salty. More tantalizingly, Curiosity's environmental sensors have shown that conditions in Gale Crater today are favorable for the formation of transient liquid brines. During cold winter nights, humidity rises enough for the calcium perchlorate in the soil to pull water from the atmosphere, forming a thin film of liquid brine in the top few centimeters of soil, which then evaporates after sunrise. Curiosity hasn't seen the liquid, but the data strongly supports its ephemeral existence. The Perseverance rover in Jezero Crater is building on this work. Its primary mission is to search for signs of ancient life in another former lakebed. It has confirmed a history where the lake slowly evaporated, leaving behind salt-rich mudstones. By collecting samples from these salty layers, Perseverance is caching the most promising materials for a future Mars sample return mission to analyze on Earth. Just when the story seemed focused on these fleeting, near-surface brines, a bombshell discovery in August 2024 reshaped everything. Analyzing years of seismic data from over 1,300 Marsquakes recorded by the InSight lander, scientists found compelling evidence for a vast reservoir of liquid water deep within the Martian crust. The data revealed a zone between 11 and 20 kilometers below the surface that is best explained by fractured rock saturated with liquid water, similar to deep groundwater systems on Earth. If these conditions are planetary, the reservoir could contain enough water to cover the entire Martian surface in an ocean 1 to 2 kilometers deep. This provides a potential answer to the question of where Mars's ancient water went. A significant portion may have simply soaked down into the crust. This deep reservoir is far too deep to access with current technology, but its implications for astrobiology are profound. It suggests a stable, long-lived liquid water environment, protected from harsh surface radiation, that could potentially be a habitable environment for microbial life. This brings us to the ultimate question. Could anything live in these Martian brines, whether near the surface or deep below? To explore this, scientists look to extreme environments on Earth, like the Atacama Desert in Chile. There, microbes survive by taking refuge inside salt rocks, using the process of deliquescence to get water. It's a plausible strategy for Mars. However, habitability isn't just about the presence of liquid. It's also about its quality. Two critical factors are temperature and water activity. Water activity is a measure of how free the water molecules in a solution are. Pure water has an activity of 1.0. As salt is dissolved, the water activity decreases. Terrestrial microbes have a hard limit for growth at a water activity of around 0.6. Herein lies the double-edged sword of Martian brines. The same high salt concentrations that allow them to stay liquid at cold temperatures also drive their water activity down to extremely low levels. Models show that when Martian brines are liquid, they are likely either too cold or have a water activity too low to support the replication of any known Earth life. This has led some researchers to conclude that while Martian brines are a fascinating geochemical phenomenon, they may not be habitable for Earth-like life. This, of course, is all based on life as we know it. Hypothetical Martian life could have evolved a completely different biochemistry, and the newly discovered deep reservoir offers a much more stable and potentially life-friendly environment. The story of Martian brines is far from over. From the illusory canals of Lowell to the microscopic seeps hinted at by modern orbiters, our search for water on Mars has become ever more nuanced. The debate over RSL continues. The discovery of the deep water reservoir has opened an entirely new avenue of research. The samples being collected by Perseverance hold the promise of unprecedented ground truth when they are returned to Earth. The fleeting chance of liquid water on the red planet, in the form of these salty brines, is a link between the planet's vibrant, watery past and its present-day state. It is a potential, if extreme, habitat for life, and it is a vital resource for future human explorers. The hunt for these elusive brines will continue to drive our exploration, pushing our understanding of the line between a living world and a barren one. Mars still holds its secrets close, but with each mission, the ghost of water becomes a little more real.